I'd like to introduce Jim Whitehead. He's a professor at UC Santa Cruz and his student, Soon Kim. They've been doing some really interesting work on looking at software evolution and data from source code repositories. So I asked Jim to come give this talk, or he kind of volunteered when he found out I'd come to Google. So thanks a lot, Jim. Look forward.
Right. Yeah, thanks, John. Yeah, John, I guess when he started working here, he's like, oh, and if any of you are ever in the area, and I'm like, well, I'm in Santa Cruz. I'm always in the area, so kind of said, come on down. I'm going to be talking about some recent work we've been doing in our lab at UC Santa Cruz on predicting bugs. And the work is done with my student, Sung Kim. There's also another professor, Yi Zhang, at UC Santa Cruz, and then my student, Jennifer Bevan, as well. And then Thomas Zimmerman and Andreas Zeller are at Saarland University in Germany, and they've collaborated with us on that as well. So the idea here is that if we can, if we know where the bugs are, before they occur, that you can take some steps to improve the quality of your code. So if you know that a particular set of files is much more likely to have bugs than some other set of files, you can spend more of your QA time on those particular sets of files. So you can do things like do more software inspections on those files, or perhaps you can run static analysis tools on those files. Static analysis tools often return a large number of false positives, and so generally you don't want to run them across your entire code. But if you know that there's a high likelihood that you're going to find bugs in some section of your code, it might be worth your while to spend that additional time. So in general, there's this kind of realm of techniques that are very time expensive that you can use to improve the quality of your code. But you generally don't want to use them because you have fixed QA resources and you don't really have a good sense of how to prioritize the application of those QA resources across your code. But if you did have really high quality data that said, I know where the bugs are in our code, then you could start doing some of these more expensive techniques. Okay, the other kind of work that we do is that we want to improve developer awareness that maybe they just created a bug. And so most of the time a developer injects an error into their software, and then it may be weeks, months, sometime later that error actually manifests itself in some externally visible behavior, and then after that point in time you're able to go and make a fix to that. And so there isn't a very strong immediate feedback loop back to the developer that there may be a bug. If you could actually provide immediate feedback to the developer that there's a high likelihood that they've just created a bug, then the developer, right then, when they have all that context in their head, could maybe go and re-review their code. Maybe they could get a colleague to do an inspection and so on, so you could close that loop a lot faster. Oops. So we have two main results we're going to talk about in this presentation here. And so one is this bug cache, and then the other one is on predicting buggy changes. And so with the bug cache, what we do is we take the software and we put it into two bins. And so typically we make the one bin, the bin of buggy software, we set that to 10% of the total size of the code. And we run our algorithm, and at the end of running our algorithm over the revision history of the software, that cache, that 10%, will contain 73 to 95% of future bugs in the software. So using this bug cache algorithm, we're able to, with very good results, tell you where the bugs are likely to occur in your software in the future. And what's nice is now that you have that 10%, you can focus your effort on that 10%. The other work that we do is we have been using machine learning techniques to analyze the changes, the individual commits, and so we're able to, we train on the entire revision history. After we have our trained machine learning algorithms, we can, given an individual file level change, so that's about, on average 20 lines that have changed in an individual file, with about 75% accuracy, we can tell you whether that's going to have a bug in the future or not. Okay.
Things don't match, how do you define a bug?
If two things don't, so which things?
So if you have, if there's a miscommunication bug between two parts of a system, where is it?
Right, yeah, so we, So what we are going by in terms of bugs are, we mine the histories, and so typically we're looking for in the change log of a commit to an SCM system. There's two approaches. If there's a high quality change log, we look for the actual identifier of the bug report and the bug tracking system. And so the developer will say, just committed a fix to bug number whatever, right? And so then we know that that particular commit contains a bug fix. Oftentimes the commit logs are not that high quality, and so we will then just look for keywords like fix, repair, etc. And so there's a small number of keywords that usually indicate that there is a bug fix there. And so we've done some work in the past where we've also gone back and manually examined these things to see, okay, are we, is this getting things that really are bugs or really aren't bugs? And it's, the techniques work pretty well, and they're not perfect, but barring actually going through, several thousand revisions of a software project and manually, inspecting each one to say whether that's a bug or not, this technique is automatable and gets us very good results for identifying what's a bug and what's not a bug. Okay, so in some respects, what we're trying to do is take advantage of the fact that use of software configuration management systems these days is ubiquitous. All projects of any consequence use SCM systems. So you build up this history of changes, and the idea is that we can learn from those changes. And especially as people are fixing bugs, they note in their change logs that they have made these fixes. And so this gives us a labeled data set. And the data set is a number of changes, and they're labeled with respect to whether they are a bug or not a bug. And so from a machine learning standpoint, we have the holy grail. We have a large data set that's labeled already for us. And so this gives us the ability to learn from this data set quite easily. So there's a couple insights. So the bottom one here, software can be classified, and this is classified in the machine learning sense. So you can do machine learning classification algorithms, and you're essentially classifying a change with respect to either it's a bug or it's not a bug. So you're classifying it into one of those two bins. And so that's one of the key insights, is that you can actually view bug prediction as a machine learning classification problem. And then you can bring all that machine learning machinery to the table now. The other insight here is that bugs exhibit some locality, that they're not just uniformly distributed over the code and over time, that there are certain files that are much more likely to have bugs, and then there are certain periods of time that bugs are likely to be clumped together in time and not evenly distributed over time. And so you can take advantage of these localities to improve your bug prediction accuracy. Okay, so for the first part of the talk, I'm going to talk about this bug caching work, and then I'm going to turn over to Sung for the bug prediction work, the bug classification work at the end. Okay, so I mentioned this a bit in answering your question, but so what we have here is we have this timeline of changes, and so this is the evolution of a particular file over time. These tick marks represent commits at particular points in time to that software, and so what you have is initially there's some software change that where the developer makes a change and injects a bug. At some later point in time, you have the observation of this as some problem that needs to be fixed. So you have an entry in your bug tracking system, and then at a later point after that, you actually have the fix that was made and it was injected. And so where we start is we typically start by looking at these log messages. Sometimes we start here, but we're most typically starting with these SCM commit messages, and then we have to work backwards to find the actual fixes. And so it turns out there's an algorithm that some of our collaborators developed, Thomas Zimmerman and Andreas Eller, which gives you the ability to, using the SCM annotate feature, to work backwards to identify which particular revision actually had the initial error in it. Turns out that there are some issues with that approach, and so we've done some recent work where we've improved the algorithm that we used here. But in general, with pretty high accuracy, we're able to work back to what the original error-producing change was. And so what's nice is that most of the work on bug prediction kind of does under the lamppost kind of work. It's easy, very easy to get this bug fix data, but it's, until recently, it's been very, very challenging to reliably get back to the bug-inducing, to the error-injecting change here. And so one of the kind of things that we've been able to take advantage of is this recent advance that allows us to get back to that. Sure.
I don't understand why that's complicated to work your way back. I mean, the source code management system is going to tell you line for line, this line was last modified by so-and-so.
Right. Well, yeah, so there's a number of problems. So one of the problems is that, you can, many lines could have been changed here, including changes that involve just cosmetic changes or formatting changes, and so that can throw you off. So if you're like, well, okay, if the majority of the lines that were changed were in revision 4, but the majority of the lines were just formatting changes, then that's going to throw you off. The other thing that throws you off is that there is no good way to map a specific line back in time. So the SCM annotate, does its best, but it can get confused. And in particular, you can get thrown off by the fact that one challenge is to try and go from a particular line to the function or method that contains it. The SCM annotate can't tell you, for example, that the function may have changed its name between when the bug was introduced and when it came later. I don't know, Sung, did I do a good job of answering that, or I don't know. So I guess what I can say is that I can go into that question a little bit more in depth with you after the fact. We sort of just have written a paper on that, kind of going into a number of the issues. I guess sort of the in some respects, once you see the algorithm that we use to get back here, it's like, well, it's relatively straightforward to do that. But people haven't been doing that, and there are a number of little gotchas along the way. Sure.
What happens if the bug-inducing gene was in a different file?
Right. Yeah. So that would throw us off as well, and we don't have a good answer to that. So there's some there's some class of changes where there might be an environmental change, and so the environmental change is what led to this change here. And so yeah, we will then kind of go back and say, well, okay, the initial change that kind of led to that bug, we're just going to track it back in that individual file. We still feel that that's useful, and we feel it's useful because even in that situation, if there are many other files that would have needed to be changed due to the same kind of environmental change, or if that kind of environmental change is occurring frequently, we're still going to pick that up. And so we may be saying that the fix-inducing change, we may get that wrong, but in some respects, our bug classification algorithm is still going to give good results. Sure.
Notice that in sufficiently large systems, you get a bias for people not understanding the whole thing and then fixing bugs in the parts that they know. So,
well, right.
Where they occurred.
Oh, right, repeatedly. Okay, so in a large system, you may have an effect where people are fixing only the code that they know and not fixing other parts of the code.
Well, fixing bugs where a bug can be not in the source, but patching around it in the code that they know best.
Right, or they'll be kind of patching around and sort of avoiding some area of the code that they don't like. So there's, in some respects, we're not, so we haven't really seen a strong effect like that in the projects that we've looked at, and we certainly know that there are these areas of the code that are kind of magic areas of the code, or don't touch areas of the code that are kind of magical, and people get into trouble if they change them. And so our algorithm would get thrown off in that we wouldn't see any changes in those magic sections, and we wouldn't flag them as being particularly buggy. And so yeah, we would get thrown off in that case. Yeah. I want to move on. Okay, so we go through this revision history, and what we're looking for are certain kinds of bug localities. So we have four main kinds of bug localities. So temporal, and so the idea here is, so first of all, let me use some terminology here. So we use this term entity. We had this problem in that we want to have a term that talks about either a function or a method. So we use the term entity here to mean function/method. So if a function/method introduced a bug recently, it'll introduce another bug soon. So the sense that if there's a problem in a particular module, probably you're not going to fix all those problems right away. That is going to continue to be problematic. this notion of changing, if you've changed it recently, we're finding across all projects that, almost invariably some percentage of all changes are going to be buggy. We've seen this as high as 78% of all changes in Bugzilla seem to be buggy. So, almost every time they touch the code, they're adding another bug. Most projects, it's around 10 to 20%. So if you make a change at all, that immediately makes it suspect. If you've added a new entity, we find that suspicious. And then if you've introduced a bug nearby in the sense that it was in the same SCM commit, or in the sense that was logically coupled, that it'll also tend to introduce new bugs soon. And so the idea here is that if a developer has some mismatch in their mental model and they're making a change, then that change will, that problem in their mental model will cause them to introduce errors in a number of different places, not just one. So what we found is that this temporal and spatial locality contribute the most to bug prediction. Okay, so the bug hash, oh, sorry, question.
What about developers? Like some developers are more likely to make mistakes than others.
Right. So we didn't use developer locality in this particular one. Developer actually does end up being one of the factors in the bug classification work. And what we find is, for some projects, it's a good predictor. Most of the time, it's actually not the strongest predictor. And I think the reason for that is, in the classification work, is that a given developer is both committing a lot of good changes and buggy changes. And so the fact that the developer touched a particular piece of code doesn't mean that that's particularly a good predictor as to whether that's going to be bad code or good code. It's essentially even. The fact that the developer touched the code means, well, it might be good and it might be bad. And so, but that may be just a quality of those machine learning algorithms that it doesn't try to make a model of developer bugginess in some sense. So we use the bug localities to take our software. So we go through all of the software, and we can use this at either the file level or the entity level. So typically we set this at about either 10% of files or 10% of functions. The bug cache operates where we have an initialization step. So we essentially take our cache, we preload it with a certain number of entities or files or entities. We perform an analysis where we work through the revision history, adding some things into the cache, taking some things out. At the end of the day, we have our bug cache filled with the functions or the files that we predict to be the most fault-prone going into the future. And so, again, this shows that you can do it at multiple levels of granularity. At the file level, we tend to do best, but it also works at the function or method level. And there's a trade-off between kind of the smaller you make your granularity, the harder it is to do that prediction. But on the other hand, you don't have to look at it at as much code to figure out where the bugs are. Okay, so in the initialization step, we start off by extracting the bug fixes. So we go through the revision history and we get back to those. We get the bug fixes. We then extract these fix-inducing changes by working backwards. And then we do this preload step in the bug cache. And right now we just do a simple, the files or entities with the largest number of lines of code. We say, well, if it has a lot of lines of code in it, then it's immediately suspicious. And it's surprisingly effective. So even after running through our entire analysis for the Apache 1.3 project, one of the ones we looked at, it's still, that lines of code ended up predicting 18% of the ones that ended up in the cache at the end of the day. Okay, during the analysis stage, we process all the revisions of the project, and so we compute hits and misses here. So, we observe where the fix-inducing changes are at a given revision. If a bug occurs in a file or entity that's currently in the cache, we call that a hit. Otherwise, it's a miss. And so, in some respects, a cache hit can be viewed as a successful prediction of the bug. So we had it in our cache, a bug occurred. And so we call that a successful prediction. For a miss, this is where we change the state of our cache. So we then fetch the file, and this is our temporal locality, and then we grab all the nearby entities and put those into the cache as well. And then we also do kind of a prefetch, and so we also add in any new entities that have been created or modified at that time. And then, of course, since our cache is fixed size, we need to have a removal strategy, and we've actually explored a couple different removal strategies for taking things out of the cache. Okay, so here's what our results look like. So we've analyzed a number of substantial open source projects across several different languages. And so the projects are Apache 1.3, Subversion, PostgreSQL, Mozilla, JEdit, Columba, and Eclipse. And what we find here is that our best results are with the Mozilla project and with the Eclipse project, and they actually get up into the 90s. It's not at all uncommon for us to be in the 80s, and then Subversion is our worst one in the low 70s. What you can see is that, at least across the set of open source projects, we end up being able to, at the file level, tell you where, which are the most buggy files. And so this kind of sorting it into, the most bug prone and the not as likely to be bug prone, this works surprisingly well.
How well would you do in the baseline case if you pick the 10% of the most complicated files?
Well, in some respects, so software complexity has traditionally been very hard to measure. Turns out lines of code is about the best complexity measure out there, and so in some respects, our prefetch is already loading the most complex files or most complex entities in, and it does pretty well. And for Apache 1.3, it was about 18% at the end. That most complex, the most complex ones ended up being the most buggy. The other thing I'll stress about this is that this algorithm can be run in a kind of in an adaptive sense or in an online sense, and so as your project is continuing to evolve, you can do your initial analysis, you can get your sorting, and then you can rerun this weekly or you could rerun it monthly, and you can be getting this updated list of what is predicted to be the most bug-prone files at that time that you run your analysis. And so it will change and it will adapt to changing conditions over time. Okay, so these are results at the file level. When we do look at the same projects but at the function or method level, as we stated, so first of all, this one ends at .8, not at 1, and so the results are lower. So the worst is Mozilla here, which is just under 50%, but we can get up into the high 60s, and hovering around 60 is not not uncommon. And so again, there's this trade-off between, well, can we, the finer we get our predictive granularity, the harder it is to do because there's, it's a smaller target we're aiming for.
So Subversion's the highest one here, and it was the lowest one on the last chart?
Right. I don't know, Sung, do you have any insight on that one? Or I don't know. Sometimes the stuff we get back is just weird. The weirdest stuff, I think, are the predictors or the features and the bug classification stuff coming up next. But yeah, I don't have a good explanation for this one. Question? So in this work, I don't think we took that into account, no. So we have done some work in the past on doing automated tracking of file function names across renames. So we call this the origin mapping or entity mapping problem. And it turns out with pretty high accuracy, you can actually figure out how these things change across revisions. But it's a pretty time-consuming process, and so we didn't run it on this one. But it could potentially be done, and Sung has a suspicion that if we did run this, that would improve this a great deal. That there's some sense that we kind of lose a lot of history and we lose a lot of information when a function gets renamed. And so if we could kind of hold on to that might improve our results a bit. So we tried a couple different cache replacement strategies. Least recently used, so the least recently found bug we unload. We change count weighted, so we unload the file or entity with the least number of total changes. Bug count weighted, so the file or entity with the fewest number of total bugs we take out. And so then the question is, well, which one of these works best? And the answer is, well, it kind of depends. So here we have bars for the least recently used for the bug and for the change. And we have that at the file level and then also at the function or method level. And what we see is that at the file level, pretty much the LRU is the best. And there's one or two cases where it's not, but in those cases, it's not that far off. But then down here, it's kind of a mixed bag. On the bug, bug-based algorithm seems to be best here, and then LRU doesn't work best there. So it depends on granularity, and it also seems to depend on the project. So one of the kind of takeaway lessons we grab from this is that if you're going to do this for real, there would be some process where you would essentially train the bug cache for your particular project, and you would learn for your project, well, what are the parameters that give you the best results for your specific project, and you might even want to go through and do a retuning effort, every month or every 6 months or something like that. Okay, so one question is, well, what can you do with this? So we'd mentioned, doing inspections or static analysis, where you can also end up giving developers awareness of this. So, there's a sense that if you're working on some code that's in the bug cache, that bug cache code is riskier in some sense, and so maybe you want to tell your developer that you're working on a risky function or method, or you're working on a risky file. So we've done some work where we've done integration into Eclipse, and you'll get some icons indicating that you're working in riskier parts of your code. Sure.
You have the concept of normalizing for the number of times the code's been touched. So therefore, if you've got a piece of code that's being touched all the time by lots of people and has 5 bugs, maybe it's less error prone than something that's only touched once and only has 1 bug. That time was a bug inducing.
Yeah, so no, we don't do that, and our defense of that practice is, if a particular file is being touched a lot of times and its absolute number of bugs is still quite high, that means you're still spending a lot of money to be fixing errors in that file. And you're still spending time there, time is money. And so, you would want to know that that's one of your problematic files, and normalizing that away and saying, oh, well, even though we're spending, 10% of our time on it, relatively it's not, not one of the problematic files. And my feeling is that's not giving you an accurate measurement or an accurate feel. So. Okay, so at this point I'm going to turn it over to Sung, and he's going to talk about the bug classification work.
Thanks. So the previous bug cache work, we can identify the file or function-based. We can identify buggy function or buggy files. But if you think about all the development process, most development process is change-based. You change something to add new features, or you change something to fix something like that. So we want to try to identify each change as a buggy or non-buggy. But if you can identify or classify each changes, it's very nice, because one thing is the prediction is pretty much localized. We're looking at only 20 lines, average changes about 20 lines of the source code. So if we identify a change as buggy, we have to look at only 20 lines of the source code. Also, the prediction is just immediate. Maybe as soon as you submit a code to the SCM systems, we automatically say your source code contains code, buggy code or not. So it's much easier to remove the potential bugs. So to do that, we use the machine learning algorithms. And we basically use 2 algorithms, naive Bayes and spot vector machine, which is implemented in Weka toolkit. And then we analyze the 13 open source projects. Basic idea of the machine learning is we can take a bunch of features with a labeled set, and then it can train a classifier. And then later, we can feed an unknown set of the features, and then machine learning algorithms can classify the instance as buggy or non-buggy. That's the basic idea of the machine learning. And for the features, if we think about the changes, so we have basically 2 files. So all the files and new files. And then between the files, we can compute the deltas, what has been changed in these 2 files. Also, the file names and directory name can be one of the features. And we also compute the complexity metrics of C and Java source code, and then we compare the complex metrics of the new file and old file, and then used all complex metrics as features. Also, all keywords you typed in the SCM logs, what you have been changed, we used all words in the SCM change logs as features. Finally, we used some change metadata, such as authors, who changed this, or when you commit the source code, that kind of information. We used every possible information between changes as a feature. And this is the list of the project we analyzed, including Apache and Eclipse server, and so on. For example, if you look at the Apache project, it's written in C language. We look at the revision from 500 to 1,000. It contains 579 clean changes and 121 buggy changes. And then the future number we used is 1,100, almost 1,100 features. If you look at the GCC project, we used almost 2,700 features for the classification. And this is the results from the classification of the all projects. Basically, we have about 70% of the accuracy with above 40 to 50 recall. The next question we want to know about is that we have used a bunch of different features from different groups. For example, we get all keywords in edited delta or deleted delta. So the question is, which feature groups are most significant for the predicting bugs? So we try to combine different features from different groups and then try to classify again and then see what kind of feature has a very strong predictive power. So this is the results from the Mozilla accuracy by feature combination. For example, each alphabet indicates the group of the features. The tilde means we used every feature but that feature. So for example, here, the tilde A means we used every feature except the edited delta, and so on. If you look at this graph, mostly they are good if you use all the features, and it's really bad if you use only new source code features. The Eclipse, we have very similar shape of the results. Here, we look at all the averaged accuracy by feature combinations. What we can find is maybe using all feature is not the best. The best is using all features, but except the complexity matrix is the best. Of course, this is average, so each project may have a different behavior. But also, one thing we noticed in here is the A and D, which means edit the delta and delete the delta, and new source code, which means all features from source code itself also have a pretty good accuracy rate. That means this classifier can be embedded in the editors. So whenever you edit something, we can monitor what you changed in the editor, and then we can also predict if your change contains bugs or not. So based on the previous experiment, you can find out the best combinations of each project for the accuracy. So again here, the best predictor combination is pretty much different based on the projects. Also, we try to look at the individual features a little bit here. I'm not sure you can read each character here, but the idea is we try to identify the most significant individual features to predict the bugs. And then we rank them using chi-square algorithms. And then also we look at if each feature is contributing bugs or non-bugs. For example here, plus means the feature is contributing to bug. minus means the feature is not contributing to bug, which means clean change. So if you look at the complexity matrix measure for Apache, obviously the delta means delta of the complexity matrix. So whenever you change a lot of source code, that means a count of line, you are contributing to bug. Or if you look at the Plon's added delta, I'm not very familiar with the Python. This is written in Python. Whenever you use the self in the source code, you are more likely to creating a bug. Obviously, we need more research to see what is really patterns in here, what kind of patterns we can find out in bug code. But this gives you like overall idea is that there is some patterns that introduce bugs.
The keywords are pretty hilarious.
Yeah.
Fixes plus 345 in Mozilla patch introduces more bugs than anything else.
Right.
But correcting does not fixes them.
And for Apache, you can make any change as long as it doesn't use if, because if is highly likely to produce a bug.
For the results here, the best features for classifications vary by project and projects. So there is no cross-project model here. Also, the best algorithm classification, machine learning algorithm varies by project to project. And what you can find is about we can predict about 70% of the accuracy and recall range. But we think this is very promising because what we used is very basic stuff. We just extract all keywords from the source code. We didn't perform any semantic analysis or very expensive the static analysis for these features. But still, we get this kind of high accuracy rate. So we think if we can apply more complicated algorithms or more future engineering techniques, we're gonna raise about 5 to 10% accuracy rate. We have much more data about this, so if you are interested in, we are more than happy to show it to you. Okay.
All right, thanks, Sung. So kind of the summary, high-level summary of the talk is that, well, it's now possible to classify files as fault-prone or not fault-prone with very high accuracy. The results that we got across many different open source projects showed that very consistently we were able to do this. And the other result is that it's now possible to classify individual file-level change. You know, on average, 20 lines of code have changed here as likely to have a fault or not likely to have a fault. And this can be done with, you know, not stellar accuracy, but still very good accuracy. Probably enough accuracy that developers might pay attention. So in my view, this raises a number of open questions. So one is, you know, we've been doing this in the lab. We've been analyzing open source projects, and we haven't tried to inject these results back into the project itself and see how this knowledge would cause developers to change what they do, how it would cause QA people to change what they do. And I think there's a lot of open questions there. So one is, you know, would this affect the accuracy of our predictions? It's conceivable that this might make our predictions get more accurate. It's possible it might make them get less accurate. You know, we're not sure what's going to happen there. We're also very curious with this fault classification work. You know, if you tell a developer, you know, dear Mr. Developer, we are 75% likely that you have just made a change. We regret to tell you, however, that we cannot tell you what that error might be or where you should start looking, right? So how would developers react to that kind of knowledge? You know, they know that it's probably right? But you know, where do you start, right? And so in some respects, you know, some of our future work that we're looking at is, can you give the developer any hint within those 20 lines where to start looking for likely places that there might be a bug? And you know, would developers like this at all? And as Sung pointed out, it's conceivable that you don't even have to wait for the commit. And you know, it could be that you're typing along there in your development environment, and then all of a sudden, you know, bing, you know, we're not quite sure exactly what you just did, but we now are pretty sure that you just have a bug, right? And so it could be the thing you just typed, or it could be something that you've done previously. And but it does seem that we can do this. And so how would developers react to that, right? do QA organizations really want essentially more bug reports? And is this information on prioritizing the bugs, into that, well, this 10% is most likely to have the problems. Is that really useful, or does that just end up being another piece of interesting but not really actionable information? So what we'd like our analysis to do is produce both interesting and actionable information. So our feeling is that you should be able to take proactive action and bring down those bug rates in those files, possibly by doing restructuring, possibly by doing code inspections and so on. But it may be the case that that doesn't work. And then, can we improve these techniques? The other open question is, we've been looking at open source projects. It's quite possible that some of the characteristics of open source development could skew our results. And in particular, we know that the pattern of people coming onto projects and leaving projects in industrial settings is generally quite different from those in open source projects. And so it's quite likely that may change the accuracy of our results. But again, it may go up, it may go down as well. So we'd very much like to try this out in an industrial setting. And in many respects, that's what motivates us to come here, is that we would like to find projects and people who are willing to allow us to come in and to run our analyses on these projects, and give you the results and allow us to also publish those results as well. So that concludes our talk, and thank you for coming. So questions? Question?
Well, so it sounds like what you said is change has risk. So I guess I don't see how you're being more precise than that general notion, which I think we all have already.
Right. Okay. So the question is, well, also we all know that change has risk. What are you doing kind of above and beyond this? Well, so what I think this work does beyond just the change has risk is that it can tell you, specifically those areas in which change is occurring, which are much more likely to have risk that manifests itself into bugs. So it is entirely possible to have files that are, especially with the bug classification work, it's possible to have files that are changing and that we don't predict them as having bugs. And so it's certainly not the case, at least for that change will necessarily cause it to be noted as having more bugs. Now for the bug cache, yeah, and the fact that a file is changing a lot is very likely to cause it to end up in the cache. But certainly for the bug classification work, it's not a one-to-one. Change means we say it's buggy. Question?
So as sort of follow-up to that, how often do you find the change prediction work that you had large changes, say more than a couple hundred lines, that weren't flagged as intentional? One of the big failure modes I can see in developers is every time it'll be able to tell that the 3-line change probably is going to bug in. Every time I submit 100 lines of code, it will say, oh, there's bug. And the bigger the change, the less useful that is.
Right. Yeah. So Sung, now you've done a little bit of looking into kind of frequency of large changes in the files, right? So in the I don't know, do you want to address that question or? So we've looked at done some look at kind of how often these large changes occur. They don't occur super frequently, but they do occur. You're right.
Yeah. We actually manually inspected all the changes in the open source case. Mostly, there are changes like 20, 39 range. But the big change, as you mentioned, the 100 line or 200 and 1,000 lines are mostly either formatting change or you change some APIs and that affects all the things. And then we found out, actually in this research, we didn't exclude that kind of changes, but in the current research, we exclude that kind of change. We think that's kind of false positives.
Really useful case would be if you can tell me for any given medium size, tens of lines change with some good specificity.
Okay, so the question was, it would be nice if you could, for kind of medium-sized changes, be able to say whether there's a bug there or not. And so, I believe my sense is we're doing that, right? And so there's, so we say that our average, change is 20 lines, but the changes that we're feeding into the bug classifier, they have quite a range there, and we haven't done a specific analysis to say, well, what is the accuracy at certain change sizes? I don't know. I guess this work has produced enough surprises that I'm not going to go out on a limb and say predict what that would be like. But my sense is that would be pretty uniform. Once you got above, say, 10, 15 lines in your change, because you would have a fair amount of data in there, and so these classifiers tend to work pretty well if they have something to work with. And so I would imagine that maybe the accuracy might fall off if you get to very low numbers of changes. But even there, with things like if often being a high predictor, they still might do a good job.
How does this behave on changes which just introduce new code? How accurate is it on those? Does it flag all sufficiently large new code changes as having bugs?
Right. I don't know. Maybe you should come up. I feel like I'm handing off half of these to you. So the question was, so how well does the bug classification, how well does the bug classification work handle additions of new code?
So it's pretty much depends on what kind of code you are creating. If the new code is something we have been seen in the previous change histories, and we identify that very similar code as, for example, buggy, then your new code will be classified as buggy code as well. But it's based on the previous histories. Did that answer your questions?
I was curious, on one of the charts, you suggested that cyclic complexity was not a good, valuable component in some analyses. But on the table, where you're looking at ifs and raises and Python, those are placeholders for cyclic complexity. So,
right. Yeah. So here's the table. So the question was, so there was a previous chart, and let's see, I think it was this one here, which was suggesting that, okay, if you look at everything if you use everything except for the complexity metrics, that produces the best result for classification accuracy. But yet, if you come down and you look at this table here and you start looking at it, for example, especially with Apache, right? And those are that's showing that at least for Apache, the complexity metrics are pretty good predictors. And then the questioner was also pointing out that there are a couple of other features in here which are good proxies for some of those complexity metrics, and they were also getting raised good. So I guess kind of two points here. One is that what we're finding in doing this kind of evolution analysis is that the kinds of analysis you have to do have to be project specific, and so it's really not possible to say train a model on one project and then apply it to another project. The only time we've seen that in the literature to work even kind of well is if you take, say, an earlier version of Apache and train it on that and then try to apply it to a later version of Apache, but that's essentially the same project, and they're just kind of treating them as two different projects. So that's kind of one answer, that we would fully expect that some projects it would work well, some projects it would not work well, and so what that bar chart was showing is that on average across many projects, not including the complexity metrics, works well, but that I would say it's not surprising that they work well for some projects. The other thing I'll point out is that it's often the case with these features that even if you run your analysis and say, well, it seems like we do a little bit better not including it in, that if you are running a separate analysis where, say let me get back to the chart so I can point here. So this may say here that, you might just want to throw out the complexity metrics, but then of course for those projects where the complexity metrics work well, you would presumably have a lower predictive accuracy. On the other hand, you might not necessarily lose all of that, in that because the machine learning algorithms are essentially kind of weighting all of these features. It may just be that even if you remove one whole class of features, it'll just reweight all the existing ones, and it still may get fairly decent predictive accuracy. And so there's a cut. It feels to me sometimes with these machine learning algorithms, it's almost like magic going on under the hood, because it's like they're able to adapt. You take out some piece of information, and it still seems to do well, and you're like, how can you just remove this whole huge piece of information or class of information, and it still does well, right? And So anyway, it's and of course it just drives me crazy. It's like you'd like there to think that there's some kind of like rational causal model for why do bugs get into the code, right? And then you look at these features here, and you're like, well, sometimes if you add if, that's a high predictor, but not always the case. And so it's not just, you can't just label if as the bogeyman all the time. And sometimes the author is important, but most of the time the author isn't. It's just and so like here self is bad, but in other projects similar kinds of constructs aren't. So yeah, it's a real head scratcher here, and so it's I guess it's kind of highlights some of the pluses and minuses of using machine learning, in that it can see patterns there that you wouldn't as a human ever have been able to pick out. On the other hand, what you get back as kind of your predictive model is just weird, right? It doesn't give you this kind of nice if X happens then Y happens kind of causal model.
Jim.
Sure.
So just to follow up on that, the deleted delta on Apache with if, right, is plus 18. So that means you're taking an if statement out.
Right.
So that's actually reducing the complexity. So you're more likely to introduce a bug in Apache if you reduce the cyclomatic complexity than if you increase the cyclomatic complexity.
Well, with Apache, they get you coming and going, right? So if you add an if, that's a really good predictor. But if you remove an if, that's also a pretty good predictor.
Is higher numbers more predictive or lower?
Lower number. So one means it's the best possible predictor, and then a very high number means it's higher. And so and then in each line you get the top 5 predictors, top 5 predicting features for that class of features. So that's why, for example, on complexity metrics for Eclipse, and they're all up in the hundreds. That just happened to be those were the top 5 best complexity metrics for Eclipse. But they, overall, in the project, they're bad predictors. It's just that they happen to be the best 5 ones for complexity.
How do you handle combinations of files? I didn't exactly get that. So you do a check-in and you change 3 files. Are you taking into account the specific combination of files that you've changed? Are you able to say something about which of those 3 files is more likely to have the bug in it that you're committing?
Right. Let me hand this one over to Sung. So the question is, so if you in a commit that has multiple files, and that's a fairly common case, does the bug classification algorithm, can it say anything about, well, are any of the files more likely to have bugs than others, or does it kind of do some aggregation across all the files and so on?
The quick answer is we didn't take an account of the code changes. We look at the individual file changes. But I think that's a good idea to look at. Thanks.
Question?
You got anything looking at predict the severity of the bugs?
Right. So the question is, have we done anything to predict the severity of the bugs? So unfortunately, no. And this is in some respects one of the reasons we would like to get into an industrial setting. So the bug data that we have to work with is not uniformly labeled with severity data, and so in some industrial settings, they are very good about labeling bugs with particular severities. And so, if we can get our hands on such a data set, we can certainly do that prediction. We just don't have that information available. But yeah, it would be really interesting to see, are we predicting all the low priority bugs, or are we predicting high priority bugs? Are we predicting them fairly evenly with respect to priority level? Yeah, it would be nice to know. It's like, are we flooding the system with predictions of minor stuff, or are we really catching some of the good stuff? And at present, we don't have a good sense of that.
Have you looked at anything about how long till a bug surfaces? So, of course, the one everybody cares about is the bugs that make it past release and get picked up by the customer.
Right. Excellent question. I'm going to turn this one over to Sung. He actually has done some recent work looking at the time between the bug-inducing change and the bug fix change. And I'm trying to remember the graph that he produced, but anyway. Yeah, so the question was, have we done any work looking at kind of the time it takes between a bug introducing change and a bug fix change, and what does that frequency distribution look like of those times?
In open source case, when we look at the real bug introducing point and then real bug fix point is average 100 days and 200 days to fix that kind of data. Also, we think some files that takes a longer time to fix the bugs, maybe it's some indication of buggy or non-buggy. So the future work, maybe we can take that into account as use one of our futures for these classifications.
And I'm trying to remember the shape of that graph. As I recall, it's like if it's a normal, yeah, but it's a normal bow just with a pretty fat middle. So there's a. Okay. Well, anyway, thank you very much. Great questions, and thanks for coming out. And we can answer lots more after the talk too.